Okay. What's the energy level in the class? Not high. How was the first assignment? How was the first assignment?
It was a lot, yeah.
It was long. It was long. It was not individual assignment, so you could have done divide and conquer, right? I mean, divide.
Yeah.
Okay, that's true. That's true. Really, was it that long? So let's see. Let me just quickly see what the. So this is just a hand computation. Should not take more than 5 minutes or 10 minutes, right? You just need to know what is the a to the power b, gradient with respect to a, gradient with respect to b. That's all. And gradient descent is just a one-dimensional problem, right? So we know, like, literally in that um, linear classifier example, you just have to delete everything and just do this one-dimensional thing. You know. It's, okay. Okay, this is fine. This is just writing a function, so that should be fine, right? This question, right? Def loss bracket some input is equal to numpy dot something. Um, okay, so this one is basically the same as before, as in the same data that we saw in the example. Um, so this is actually the solution in the class, right? I mean, you already have multi-class logistic regression, and L2 regularization is also there in that code. So you just have to run it. So this part, I guess, is new, which is cross validation, right? That's a little bit of work. Any questions? No. Yeah, I mean, so these questions actually don't have to be too elaborate. Okay, just you can answer in one few sentences. One or two sentences is good enough. And the next one is saying use Keras and TensorFlow is the same thing. I mean, right? And solve for MNIST. Um, we did not talk about TensorFlow at all in the previous lectures. So I'm fine if you had done it with PyTorch. It's not a big deal. But TensorFlow is just that you need to understand a slight difference, like session.run, or in a session how to run a computation graph. But actually, if you see, I mean, I think sorry, yeah, the basic classification code there literally tells you how you derive a simple linear classifier, right? Or a one with some nonlinearity like this. Here, the only twist is that you need to use a leaky ReLU. That is a little bit non-trivial. But if you're going to use TensorFlow, they already have different nonlinearities. I don't know. Did you guys use that or no? Okay. Um, yeah. So it's a little bit, it's for 2 weeks, so I think it's fine, right? So any questions about this difficulty level? I mean, next we'll get into more interesting projects. Okay. Today we're going to start NLP. Some of you know NLP beforehand, but for some it's going to be new. So we'll deal with how to deal with text. And today's lecture, next lecture, is about language models and all the cool things that you've been seeing from OpenAI, the GPT-2 model, and all that. They're all related. Okay.
Yeah,
Anyway,
I have a question. Can you scroll up to number 3 and see what
yeah.
So for this one, we don't have to generate any data, right?
Nothing. It's just a definition, function definition,
That's right.
and add two things to change the definition a little bit.
Just start with generate data.
Not needed. I mean, try to do the minimal but succinct and
Right.
just enough work. Okay. You can of course do more things. Explore around with your Jupyter notebook. That's for your understanding. Okay. Okay. So that's good. Let's come back to. So actually, I had a few things to say, but let's see. I mean, just housekeeping items. So let's see. So quick check. Question zero. How many of you haven't yet logged into the server individually? Your team may have, but who has not yet logged into the server? Not yet. And what's stopping you from logging in? Because you should, get used to this workflow. Like you need to get comfortable with like not logging into the server, at least connecting to the server and starting Jupyter notebooks. Irrespective of whether you rent those machines from you get it from CBA or AWS, you may have to do something, and the faster you get acclimatized to this type of workflow, the better. You know, you can just run, it may not be a GPU based task, so it may be a large data set. You can spin up a server on AWS, run some quick computation, run your R scripts or Python scripts and get some results and close the machine. Okay, it's going to cost you $1 or $2, but that's the scale at which the large data, big data, you have to do this. You cannot do everything on your machines. Okay. So try to get that going soon. Who has not yet tried Collab, Google Collab? Because we just did PyTorch. Literally, the PyTorch tutorial GitHub link has open in Collab link right next to each tutorial. So who has not opened Google Collab? Why not? You should do it. I mean, so if you can clone that repo and open in Jupyter, that's fine. But I would suggest. I mean, Google Colab is not necessary that use Google Colab. You can use a Jupyter Notebook and the server that we have, but at least clone it and run through the example, linear regression example. So, okay. And second thing is our servers. They are they can turn off anytime. So don't try to. I mean, if there is any precious data or code, back it up. So the question is, how do you back it up? Create a Git repo, okay, on GitHub. It's free. Commit your Python notebooks onto. Keep committing your notebooks onto the repo. Keep pushing the repo to the Git repository, the remote repository. In this case, the GitHub version. Okay. So how many of you are not familiar with the Git workflow or Git version control? Many people are not familiar. Who's familiar actually?
GitHub, I know GitHub.
GitHub, yeah, GitHub, Git, same thing. I mean, not the same thing, but GitHub is a service for working with Git repositories. But so maybe I will try to do something. We'll see. Uh, so anyway, I guess there it was not so much about Git. Actually, the 2 points there. One is the servers can lose data. So the data part, like CIFAR10 or maybe some text data that you collect, if it's gone, it's okay. You can download it from again. Okay, typically it's already curated. The codes that you're writing, at least your versions. I mean, if you're just replicating and running somebody else's code, that's okay. If it's lost, okay. And your but I would suggest having this Git workflow just so that you don't lose your especially if you're doing projects on these machines. These are not reliable. These are consumer grade machines. What if suddenly some parts fail? We don't know. Okay. So that's why people, I guess, prefer cloud, because there's some guarantees on availability and fallback. Anyway, so that's that. The second part was, of course, Git workflow. Get used to that. Um, yeah. And projects quickly. I mean, I just wanted to spend just 1 minute on projects. So some people have started thinking about projects. A couple of people have contacted me. So let's start thinking about projects. That's the fun part of this course. Not the boring lectures that that we have every week, right? So think about some interesting projects that you want to do, or there's already a project thread. I think I pinned it on the forum. How many people visit the forum? Okay. Let's see. Yeah, the project ideas thread is pinned here. I don't know why this is not pinned. Maybe. Oh, unpinned for me. Okay. So actually, I pinned three things. Internship opportunities. I kind of, if I get something, I'll just post it here. It's up to you to look at it. Recent developments, you guys can post also if you find anything. every week there's some new stuff going on. Okay. um, and then project ideas is a thread. I think last week I suggested a project which is related to generative adversarial networks, right? This stuff. um, and there's also, for example, a Kaggle competition running with something to do with images and autonomous vehicles. So these are all things that you can use. You don't have to cook up your own project. You can if you want to. That's fine. So start thinking about your projects. Now, with that said, let's come back to today's lecture. And today will mostly be NLP, but the first 5 minutes I'll cover something from last lecture. Okay, it's dropout and regularization. There's a script. I'll just at least open the script. Okay. Actually, let me do that and then come back to. Oh no, that's so. So before, so today's lecture I'll start 5 minutes later. I'll tell you um, what the lecture goals are, and then we'll go into the NLP part. But for the first, couple of minutes, I just wanted to show you from last lecture. There's one, I guess, link that I did not add. I think last time I just added it recently. So it's basically about overfitting and how dropout, any sort of regularization can help you. Okay, mostly we looked at two regularizations. One is obvious L2 regularization on the weights. The second regularization is through dropout. And this is from actually TensorFlow. So we have not been emphasizing TensorFlow so much on this course, except for that one problem where I said use Keras, but that's easy, right? This is in TensorFlow, so you'll have to install TensorFlow. So in the default Anaconda installation, it doesn't have TensorFlow. It didn't have PyTorch, right? Remember, we ran some ran some commands to get PyTorch installed. So if you install TensorFlow, you can install TensorFlow -GPU. Okay, that will use the GPU version. And so if you do that, then what is this called? Overfitting. Yeah. So this is literally a script from TensorFlow's tutorial pages. Okay. So it's basically trying to show you how overfitting and underfitting can happen. So I think before this, we'll not go into the details of the all the TensorFlow semantics here. It's about, I think this is about. Yeah. So IMDb movie reviews, I guess, and sentiment analysis are basically movie review classification problem. And so it's a usual script you can run and understand what's going on. And it's a different API. So let's not go into the details of how they're doing it in terms of downloading data and all that. So okay, overfitting. Keras you just use, so you know how to create layers, right? So here's dense, dense, and then one dimensional output. Sorry, it's not one dimensional output. Oh, review predict. I think they're predicting the review score maybe. No, it's actually. Oh yeah, it's a sentiment classification problem. Um, and they're giving an output, single output, because they want to do a different loss function called binary cross entropy. It's not different. Binary cross entropy is the same as cross entropy for two class problem. There's a different function here. That's all. Okay. So cross entropy loss that remember, sum over y times log of the predicted probabilities is the same thing. Anyway, so oh, it's not executed. Okay, let me execute it. Um, I hope I have TensorFlow here. Yes. So actually, I was running it on a different machine, probably. Anyway, okay, baseline model, some warnings. Something is deprecated. Okay, that's fine. Okay, sorry for the delay, but I thought I had run it and saved it, but it was not. Um, Actually, the nice thing about TensorFlow is the tensor board aspect. I think with PyTorch also you can hook into tensor board. Um, Anyway, so that was the base. So what we're trying to do is train different models. Okay, so first we train. So in the previous cell we trained something called a baseline model. Here we are training a slightly smaller model. Okay, um, and then a bigger model, and then the rest of the code. Yeah.
Why do you use different activation functions? So the new value in the first two layers, then you suddenly switch to sigmoid.
Oh, it's sigmoid always in the last. I mean, it's not really a non-linearity. Where does it say? Here, this one.
Right now, I was wondering, so why is it relu in the first? Okay, I understand. I can get why it's sigmoid in the last layer because it makes it binary, but why is it a different activation in every?
It's not different. No, it's relu.
And then, okay,
No, no, sigmoid is because they did not have to do this. Okay, they could have done dense two as the output, and they could have used cross entropy here. That would have included the softmax operation. Like you get two scores, two class classification, two scores, and then they get transformed, right? Here it's just one number, the activation at the end, and they're just doing a sigmoid. Yeah,
So if we have one output, we use sigmoid instead of softmax.
doesn't have to be. So you can have one output for a regression problem, for example. Then you would not use any further softmax, right? So no activation there, no sigmoid, and then the loss function will be just square loss, for example. If it's regression, you will still have one output. Here it's a binary classification problem. Yeah, they have a single output here. They're doing a sigmoid transformation and then doing whatever it's called, binary cross entropy loss. Okay. I mean, this is just. I mean, you don't worry about this. Just always use cross entropy and always produce the number of classes is equal to the number of output rows in your last weight matrix. Last fully connected layer. Uh, well, I should have done all this. Let me run everything. Okay, that was too much. Um, yeah. So I guess interesting plot is going to be this. I mean, also get used to matplotlib. It's very simple. It's a little bit easy. You can just call plot bracket x. Let's say x is a numpy array. It'll just plot something. Okay. Um, and you can always give these keyword arguments, labels, and titles, and so on. Colors. So anyway, so what we want to show is this curve. So in I think in 575 I kind of draw these types of curves where you have loss going all the way to zero, and then and, and we just figuratively say that the test error, in this case it's just a validation error, is going up. Okay, so you can see that as you're training more, as you're fitting more and more and more, the error is here is zero. Okay, whereas your out of sample error, basically the validation error is going up as you overfit. Okay, so yeah, and you can also see the trend here. I think the blue is the baseline. So this is some original network, a network smaller than this, and a network bigger than this. So bigger network is like really messing up in terms of this validation error, or basically the training error. Sorry, test error. Whereas the smaller network at least is not. I mean, it's less horrible than the baseline. Okay. So I guess a smaller network means less capacity to overfit. So that's what we investigated here. And then the next, I guess, let's just directly go to the plots. Here they're just showing the difference between L2 regularization. So again, you have a baseline, the same original baseline, and then you're saying, okay, if I regularize now, same network. Now it's not the smaller network. It's not a different network. Same network, but now you have in your training, you have additional, in your objective function, you have a different, additive term. right? That square loss. Sorry, you have the binary cross entropy loss, and then you have the regularization term on the weights. Okay, that's at least pushed. Of course, then if you have a cross and the regularization term on the weights, then this thing will not go to zero. You see the orange curve, right? Orange curve will not go to zero because that's you cannot have um, um, if you make the weight zero, then there'll be a loss for sure. If you make the loss zero, then weights will not be zero. So the sum totally, is not going to be zero. But although here he's just plot of, I guess, loss only. Anyway, so from baseline you can do better if you do regularization. That's basically the gist of this plot. And still, but I guess the interesting thing is you still have a huge gap between training and test. Okay. But what matters is the test performance, or validation performance in this case. And finally, we look at the impact of, so that was with L2 regularization. Now we see impact of what's it? Dropout. So dropout is very similar aspect. So it's restricting the capacity from baseline. It's doing better. Okay, that's the idea. So, any questions about this part? Like, no, you're perfectly fine with like doing better than baseline with adding regularization. So you can ask like, why is this trending up? I mean, is this not alarming? It is alarming. Okay, you don't want to, you don't want this curve to like really trend up. Okay, you want it to be like maybe flat. Flat is better. I mean, flat is better, or maybe if you have a validation score, for example, the model that you got it after 5 epochs is probably better than the model that you got after 20 epochs. Okay, because in terms of validation score, the validation score for the model at the 5th epoch, before you keep updating the weights with grain descent or whatever it is seems to be better in terms of a held out data set. Okay, so those are things that you need to think about. In addition to, of course, the gap between why is this, orange curve above this orange curve, like how should I be even focusing on trying to narrow that gap or not? Those are all questions that you need to think. Yeah.
And then maybe you're going to talk about it. When should we try to do that? Because sometimes you'll get better training validation accuracy,
Yeah.
even though the model says it's overfitting. Like
Oh, no. So this doesn't mean overfitting. Okay. This doesn't mean. I mean, okay. Yes. This okay. This means that the training loss is zero, but that doesn't mean. There's a slight distinction between what is meant by overfitting and setting the training loss to zero. Okay. Um, so of course, setting the training loss to zero means perfect prediction on the training data, but that does not always mean that the model has actually overfit. Like for example, think of a linear case, right? If all the x versus y, the points are exactly on a line, even though I don't have intermediate measurements, right? Like something like this, right? Oops, this doesn't right. Um, uh, okay, anyway. So if I have, let's say, 3 observations like this, right? And I fit a line, okay, because exactly this is zero training loss, right? Doesn't mean this is overfit, right? Although I don't have intermediate observations here, whatever the observations are, doesn't mean it's overfit. But I agree. So you're overfitting, as in you're setting the training loss to zero, doesn't always imply that validation loss is going to go up. It could also go down.
Ones are validation more successful or even
Yes.
good performing, it doesn't matter.
Yes. So actually, like as we like this year, for example, last year, people are investigating these regimes of training. So in 575, for example, people have and we kind of think of that we should not. This means like we have really overfit and we'll have high error. Okay, but that's a little bit of a misnomer, I think.
Is that only okay? Yeah, you showed one here. I was going to say that.
So this would be called an interpolating model, in the sense that it literally is zero error on the training data, but it doesn't need to necessarily have a bad validation error. Yeah. But you need to monitor validation scores. That's it. So the training curves don't really matter. It doesn't matter whether it's went to zero or did not go to zero. Just focus on this and try to push that curve to as low as possible if it's a loss type of function. Okay. So it's a good question, and in fact, some people are working on simple models where you can have zero training error and still have good validation error. Like trying to understand overfitting and really well, and it's recent development. So in a sense, the research paper is just being written about this. Yeah. Okay, so this was a script. So you run it when you have time, but you'll have to install TensorFlow for this version. It's okay if you don't want to take the burden of installing TensorFlow, but you should try it. It's an interesting challenge. Okay, I mean, since you're investing time, invest time on this as well. Okay, next. So with that, took some time. So let's go to natural language processing. So how many of you have done a course on natural language processing? 2 here. Yeah. So last semester or semester? Last semester. Okay. So you guys should help me because I'm not an NLP expert.
So I haven't done the course over here, but then
You've done it somewhere else.
I've worked on.
Yeah. Yeah. So you should help me. Both of you should help me, and maybe you also. So, so today's objective is actually quite not too lofty. So we're going to understand some elements of natural language processing, and then understand some simple methods. Okay, I call them simple methods, but they might not be too simple actually. Many ways are simple. Latent initial allocation. It's for topic modeling. You have a corpus of data, 10 SEC filings or reviews from Yelp or whatever it is, or IMDb movie data, movie reviews, and then you wanna doesn't have movie reviews. It can be anything, news articles or whatever, and then you want to model what topics composition is there in each document. Okay, that's what we'll do. That's a warm up. Next, we'll look at we can use CNN for textual data as well. Okay, and one example, and in fact, there's a script that if I can, I'll try to run, which will use the CNN for sentence classification. Okay, it's just a sentiment analysis task, same as I think. Same as that IMDb problem that we just saw. Okay, so this data set that we just saw, overfitting data, it's about two-class classification. Given a IMDb movie review, is it positive or negative? That's essentially what it's trying to do. And then the last thing is from this notion of embeddings of text, embeddings of words instead of images. Okay, so images, remember the last pretty much the last activation layer. Last fully connected layers outputs, we were calling them image embeddings. Similarly for words, also there is going to be what are called embeddings or vectors, and we'll see one way to learn those embeddings. Okay, so that's the goal. Is the goal clear for NLP? Okay, so let's start, and I hope I don't get disconnected from Wi-Fi. So, sorry. So before I get into NLP, there's one, just a teaser for like one other CNN. So this is a famous CNN, I guess from 2 years ago, called DenseNet. Okay, so I mean there are actually well-known CNN pre-trained models in Torch Vision, so you should download them, ResNet 18 and so on. So DenseNet is just a CNN where what they're trying to do is, so ignore these curvy lines. So all they're saying is there's an input tensor, some CNN layer, convolution layer, max pool, another tensor, on layer max pool, another tensor, on max pool and another tensor, and so on. Right? Now all they're saying is the first tensor that I produce from, let's say, the first layer, I'm going to not just feed it to the next layer, but all the subsequent layers. Okay. The same tensor is just being produced as in fed into the subsequent layers. Okay. Now, how do you add them? I mean, how do you feed them? Like, for example, for example, this guy is. Okay. So this is the layer. The white thing seems to be the layer. Anyway, so there's a red curve coming in. So this tensor is going in here, and the green computation is also going in here, and then some output is produced, right? So you can do two ways. You can concatenate those tensors in some weird way, or you can add those tensors if they're the same dimension, and then pass it forward. Okay, and they're claiming that this helps in literally in the abstract. They say there are so many direct connections, and it helps in things like vanishing gradient problems, sampling feature propagation. All the claims they're making it, and they show it empirically that it kind of works. Okay, so this is the type of research from 2 years ago. Just a example. Okay. Anyway, so today 3 parts. NLP tasks, what are they? What do they look like? And second part will be simple models, LDA mostly. That's the core we'll try to revisit, and then word embeddings and word to vec. Okay, those are three parts. So okay, let's skip these types of things. Let's directly jump to an example. So yeah,
The what to vector and count vectorizer are they different?
count vectorizer. What is that? Is that a
Yeah,
function in your torch text or something? I don't know.
they are different. So count vectorizer is just a simple Python counter function which we use, right? So
Oh yeah.
so if you have a vector, it will actually give you a dictionary as an output.
Yeah. Counts of the number of elements and
Yeah, where
yeah.
the
Okay.
key would be your word and
Unique elements and then how many times it repeated.
frequency
Okay.
would be your
Yeah. Sure. No, it's not the same. It's not the same. That's fine. Okay, so just first few slides examples. This is Google Translate, English to anything actually. In fact, I think there's a assignment question which is asking you to pick your favorite language, maybe your mother tongue, and to do the translation. Okay, using RNNs. So that's I guess 2 lectures from. I mean, the deadline is 2 lectures from now. RNNs we'll see next lecture. Okay, but you get to play with this. Uh, and some other, I guess that was a product which is actually a commercial product. There are people working on these types of problems in research. For example, query answering. We already have text corpus with different articles, like typically news articles, and you want to ask intelligent questions. In this case, like the article is talking about a couple of people, and then say, in this case, there's this very nuanced question, and there's an answer to this. This need not be need not be only achieved by deep learning or something like that. This could be you may construct what is known as a knowledge graph, okay, and then answer relationships between what I call entities and so on, and then answer this, okay. But the problem is interesting, and people have different approaches. There are deep learning approaches as well. Uh, it's not really text. Text is there here, of course. So you go from speech recognition to a language to another language and another speech. So text is here to here, the translation. For example, Google Translate maybe, right? Uh, and even visual question answering. So previously there was text and then the text question. Here it's a visual, image or a video, for example, and you can actually directly think of it this way, right? Think of a product where you have footage, surveillance, for example, or security footage of your whole thing, and there was a robbery which happened. Literally, you can ask a question like, "What was the robber? Like, what did the robber do?" Or and maybe the machine can answer something. But of course, it depends on you having training data and all that to actually train the whatever the model is to be able to get to there. But it's possible. Looks like okay. At least on demos, people are able to do it. So let's see. But there's a lot of issues with text, actually, with natural languages, which is the meaning. Okay? Meaning, the computers really don't know the meaning. At least we think they don't know the meaning. For example, he kicked the bucket has a meaning which is not literally kicking a bucket, but something else, right? And for example, here, even we don't know what this means. Like, for example, the ball did not fit in the box because it was too big or small. We know what this is because if the ball did not fit, the ball is bigger than the box. Okay, so we know which one is what. Okay, whether the box is big or small, or whether the ball is big or small, we know, but it's kind of harder for computers to uh, kind of disambiguate these things. So I'm just saying these are examples of places where in natural language things may trip, and in fact these are quite contrived. You will see that even simple things it's hard to do with text. Okay. Anyway, so let's start with the first. I mean, that is a very quick introduction to NLP. So actually, let me. Where is it? Okay. Actually, if you see on our syllabus page, there's this link to Spacey. Spacey is an example. I mean, some of you must have heard of NLTK or Core NLP. So Spacey is in the same space. Okay, it provides you a really nice bunch of functions to do things like tokenizing, and there are already built-in things to do, like for example, name entity recognition and so on. So let me open that page. So this is actually not the main page. This is a Spacey 101 page, just to show you what are the NLP tasks. So because I will getting into some other things like Naybase and LDA, but I want to show you if it works. Why is this not working? What happened? No, I don't know what these are, but I have an issue with opening this. It's okay. Uh, okay. I wanted to show you some things. Okay, anyway. Okay, actually, I just wanted to show you the list of types of problems that you can that are there in natural language processing. Anyway, that's there on that page. Click on it, and you'll see there's a nice table of different NLP tasks, okay, including simple tasks like tokenizing and lemmatization and so on, which I don't think I'll go into here. I just want to show you uh, one example. For example, here, there's a sentence, and we can find for each token in this particular sentence uh, what is its part of speech, for example, and what is its dependency. You can get a dependency graph. Like, I don't know if you've seen dependency graphs for text sentences. That's captured here. And here, I just wanted to show you. Like named entity recognition. Named entity recognition just means that given the input data, in this case a sentence, you just have to identify those words, nouns, and identify them as an entity. For example, a location or organization in a person's name or things like that. So here you can see the name of the person, the organization, date is being recognized, right? So these are some examples of things that you can do with Spacey. So I guess that's my quick introduction to NLP. Any questions about tasks? I mean, we'll get into the modeling, machine learning models soon. So I just want to give you a flavor of what things you can do with Spacey. Okay. Um, actually, that web page is not opening here. So yeah, maybe in the break I'll see if I can open it. But anyway, natural language processing is a very interesting area. So first we'll start with some older generation models where they don't kind of use word to vec, or basically this word embeddings that I was talking about. Okay, so that's what I roughly mean by saying they don't explicitly account for word-word relationships. So these embeddings that I'm talking about, they somehow take context into account and give vector representations of words such that words that appear in similar context, they have similar vectors. Okay, so that's what they do, but we'll get there. Before that, we'll look at a sequence of things. We'll not look at conditional random field because it requires its own information. So we'll look at name-based Markov models, LDA, and then CNN-based model. Okay, for now, and then we'll get to word to vec. So, how many of you have heard of name-based? Everybody, hopefully, right? Everybody has heard of name-based. So, very quick overview. Uh, or does anybody else want to give me an overview of what name-based is? No. Okay, naive-based model is a very simple model. It's just saying it's a think of a classification problem. So you have class labels and you have features. Okay, and naive-based classification, the naive-based model, the assumption is that condition on the class, the features are independent of each other, which is just this. Okay, condition on the class, in this case spam or whatever, something else. Each feature is independent of the other one. Okay, so if things are independent, you'll have a product distribution. This is a product distribution. Okay, that's all. That's naive-based in one sentence. And then how do you classify given a new bunch of features? You just use Bayes rule. You hopefully have an estimate of this guy probability of spam in your data. You may have an estimate of this conditional probability, so that you can multiply these guys together and get an estimate that this is a spam given the feature vector. Okay, so let's concretize this. Let's fix the. So let's say in my vocabulary there are only 20 words. Okay, then think of W1 to W20 to be just indicator variables of whether the word is present or not. Okay, so my universe of words just represent only 20 words. Okay, in reality there may be a lot more. So that's it. So it's just asking, given the presence or absence, think of it as a one hot encoded vector. Okay, given the presence or absence of a certain word, tell me whether that email is spam or not. Okay, that's the question. You can do that by figuring out what is the proportion of spams in my email in general. Maybe you'll estimate it from data. It's not training data. You'll also estimate what is the probability that the word is present or not, given that it's spam. Okay, so that's a like conditional probability estimation again from historical data. Okay, so yeah, so this picture, what we just discussed, except what is the use of this picture? This is called a graphical model. We're going to talk about graphical models quite a bit towards the end of this course, but graphical model is nothing but things which are connected. These things which are nodes of a graph are the random variables, and edges between them are capture the relationship between them. In particular, we know the relationship given probability of w's. These random variables are not related to each other given this. Okay, somehow this is capturing this. We'll go into the details later on, and succinct notation. This is called a plate notation. Okay, where the multiple copies of random variables, they all very similar to each other. Then you put a box, wi, and I is equal 1 to n. Okay, this is just a convention in this field. Anyway, we'll talk about graphical models and plate notation later. Several lectures from now. And estimation probability of a feature being present given the label. Just count the number of times feature was present for that label divided by the amount of labels. The type of label. If, let's say spam is 60 of your emails were spam, or 100 emails, then ny is 60, and let's say the word let's say D or something. So you can just ask whether the word and it was spam divided by the number of times it was spam. Okay, that's the type of estimation that you'll do. Okay. Anybody confused about Naybase? Or not confused, right? Yeah. Okay. So that's Naybase. It's very quick. Now let's think about the next model. Okay, Naybase was just for classification. You wanted to do class, yes or no, or you can do other things also. You can do multi-class classification as well. Now the next task, this is a different NLP task. So Naybase can be used for literally for email spam classification. Okay, that's why it was in the text component. Now the second task is what's called building a language model. Okay, so what is a language model? It's a model of what word or what character or what sentence comes next given the previous sentences. It's like the likelihood of something else happening, like the next word coming up given the previous sentences. Kind of useful, for example, when you type on your phones, it's predictive text, right? It's suggesting what could be the next word, right? And also language models are kind of integral components of I don't know if modern speech recognition systems, but definitely the little bit older generation speech recognition systems, language modeling was a very important component. Okay, to go from speech, speech signals all the way to the text, signals, you needed language model. Um, so in the simplest level, what do we need to do? It's just a very simple idea. We'll assume that so we'll kind of build a Markov chain. Okay, so Markov chain. So it's a chain over what? In this slide, I'm showing it's a chain over alphabets. Okay, the alphabets are 26 alphabets. So it's a chain over the 26 alphabets. It's not really correct here, but okay, it's not that. Okay, I didn't want to do it that way. So you can always make it on a single alphabet. If I picked a fixed order of 1, then it would be a Markov chain on each alphabet. Given the previous alphabet, what is the likely next alphabet, for example? Here, I'm just showing you compute, given the previous some information. In this case, the previous information is the previous 2 characters. Okay, so it's the 2 characters determine the state. So it's not 26 states, as I was saying. It's 26 cross 26 states. Okay, all the pairs of 26 choose 2 states, okay? Or maybe cross if it's order relationship is important. So given the previous 2 characters, what's the probability of the next character? Okay. So literally, so for each pair of characters, you compute all these 26 probabilities, right? So the 26 numbers just for every 2 characters, and then there's how many 2 characters? Depending on if you care about the order, it's n times 26 times 25, right? So those many numbers are the model parameters here. Okay, given all those parameters, now you can generate language into the future. And given that if you know the previous two characters, you can predict what the next character. You can sample the next character, get the next character. Then again, given the two characters, again sample the next character. Right. So that's it. That's a Markov model based language model. Any questions about this part? So I just told you what the use of a language model is. Typically predictive text as well as other things. Yeah.
I get it, but for when you're trying to compute the probability of was it L given that HG.
Yeah, is this letter versus given these two?
So which if you're really running this, would you basically figuring out the probability of everything, every letter in your alphabet there, and then picking the highest probability?
Yeah. I mean, you can do that deterministically, or you can sample from that. So you have a probability of L given HE, you have a probability of A given HE, you have a probability of Z given HE. So you'll have a 26-dimensional probability mass function. You get a sample from it. Typically, if you want to generate different futures, you can always take the max if you want to, as well.
But we're basically just trying to pick way off that.
Yeah. I mean, I'm not telling you. So this is just a model. So the model kind of is an integral part of various different tasks. Okay, it's actually useful for even other NLP tasks that we will see. Like it can be used. So language model is kind of a core model that you can use for many different tasks. Like even for let's say sentence, what is it called? Sentiment classification. You can use a language model if you want to. Okay, to add more. So language model, think of it as like some sort of all the prior knowledge about language structure and sentences that you see is compressed into the model parameters, and that can be used for any downstream tasks like classification or other things, even clustering or any of the tasks that you want to do with text. Okay, it's like the pre-trained model type of somewhat equivalent to a pre-trained model. So I was just saying that text you can sample, but as I said, you can also take max. Okay, then you'll get a deterministic. Exactly. Let's say L is the probability of L after HE is the highest, then you'll always get L after HE if you do it. If you do the max. Okay. Okay. So the next model is actually a little bit more interesting. So how many of you have already seen latent Dirichlet allocation? Few of you. Some of you have not seen latent Dirichlet allocation. Okay. So since that particular name, latent Dirichlet allocation, has two important things. Okay. At least, I mean, allocation is not very critical. Latent and Dirichlet. Okay. So let's talk about Dirichlet, the word. I mean, so in this case, it corresponds to what is called a Dirichlet distribution. Okay. We'll talk about latent pretty soon in the next slide. So let me just motivate what is a Dirichlet distribution first. It's a distribution, just like Gaussian distribution. Okay. So it's a distribution whose support, like remember, a Gaussian distribution support is, let's say, a single normal distribution. Support is minus infinity to infinity, right? Let's say Gaussian with mean 0 and variance 1, right? It can take any values between minus infinity and infinity. Similarly, a Dirichlet distribution, its support is basically what is called a simplex. Okay, simplex. But in this diagram, it's this triangle. Okay. So that's the support of this distribution. Support just means that all values that you sample, if you sample from a distribution, you get a realization, right? That has to be within this, it has to be a number on this triangle, okay? So what is this triangle? It's a simplex. So let me draw what a simplex looks like. Think of these as 3 dimensions, z, x, and y. And a simplex is this triangle, okay? Something which is like not on the so this is a 0 area, and this is 1 0 0, this guy is 0 0 1, and this guy is 0 1 0. Okay, so there are 3 points, right? It's a plane, segment of a plane, I guess, and that's a simplex in three dimensions. Okay? And from similar distribution, it has to be exactly a point on this shaded region. Okay, the origin is there, which is not on the simplex. Okay, so what properties does the point on the simplex satisfy? That if there's a point, let's say x on the simplex, then there'll be 3 numbers, right? x1, x2, and x3. It turns out that they sum to 1 in this case. Okay, you can see for at least the corner points, right? They sum to 1. 0 plus 0 plus 1 is 1, and 1 plus 0 plus 0 is 1. So I mean, it turns out that all points on that plane are essentially the sum of the points values is 1. Okay, is it clear? Okay, and this idea you can extend it to higher dimensions. You can't really visualize them, but so what's the cool thing about Dirichlet distribution is that it's a distribution over probability mass functions. Okay, because you can think of this x1, x2, x3 is a particular three-dimensional PMF, right? Because they're summing to 1. So think of a three-sided coin, heads, tails, and something else. Then those, those three numbers could be the probabilities with which that three-sided coin is taking heads or tails or something else, right? So a sample from a distributional distribution is a distribution. It's just a probability mass function. Okay. It seems loaded, but all it's saying is it's a sample from a distributional distribution is a vector such that the sum of the coordinates is 1. That's all. It's a vector whose sum of the coordinates is 1. Fine. So this point is going to be important when we talk about the latent Dirichlet model for topic modeling. So let me tell you what topic modeling is. So we'll come back to Dirichlet in the next slide. Topic modeling is it's an unsupervised learning task. So far we were talking about mostly supervised learning, but let's we are switching gears for at least this segment. We're going to talk about an unsupervised learning task. So here we just have a corpus of documents. Think of newspaper articles, okay, CNN.com, whatever, or New York Times. And given those documents, you just want to unsupervised learning, no labels. You just want to understand. You just want to cluster them essentially. Okay, you want to kind of cluster those documents into certain types of articles. Like, for example, some articles which are talking about politics, some articles about religion, some articles about sports. Okay, that's essentially what you want to do. Okay, if these documents, these documents are essentially the sequences of words, right? So if you had some vectors representation of these words, maybe you can just do clustering. But here, the twist is that you have sequence of words. So how do I find these topics? Okay, how do I find these topics in an unsupervised manner? Here's an example. So here's a document. Okay, it has some bunch of words, one to n, and you can ask. So essentially, you want to answer the question: what is this document about? Okay, you can say, oh, maybe it's 50% weather, 50% finance, and very little of sports. Okay, so now you're not just saying that this document is exactly just politics or something. You're saying this document has some percentage weather, some percentage of finance theme in there, and some percentage of sports. Okay, why is this useful? Because if you have these ideas, then maybe when you do a search over these documents, you can probably thematically, even if the words, if you search for some word related to finance and that word is not there in this document at all, but since you know that this document is maybe has a theme of finance, you can return that as well, for example. Anyway, there's a supervised learning task with various users. Okay, and now I'm going to describe, there's a lot of text here, but I'm going to describe what is called a generative model. Okay, a generative model, and this again goes back to this is an example of also a graphical model. Okay, so remember naive Bayes is an example of a graphical model, and LDA is also an example of a graphical model. In fact, it is a latent variable graphical model. Okay, so I'll tell you what latent variables are. So what is the generative process? Let's understand generative process. Okay, so first you sample a random variable from a Dirichlet distribution. You sample a value from a Dirichlet distribution. Okay, Dirichlet distribution will have some parameters. In this case, I've written it as alpha 1 to t. Okay, think of t as like 3. Okay, capital T is 3. So I only have 3 topics. Okay, what were the 3 topics? Weather, finance, and sports. So Dirichlet somehow has 3 numbers as its parameters. That's not very critical here. It has 3 parameters, and you draw a sample from it. Okay. Now that sample, it will also be 3 dimensional. Okay. So it's theta 1, theta 2, theta 3. Okay. So what's the specialty of this sample? It's a distribution. It's a probability mass function. Theta 1 plus theta 2 plus theta 3 is equal to 1. Okay. It's a distribution. Okay. So that's interesting, and don't worry about these sentences. But anyway, so there's 3 thetas that I got: theta 1 plus theta 2 plus theta 3, and they sum to 1. And as it says here, alphas are supposed to be called hyperparameters, and theta is a distribution over topics. So theta is three-dimensional. Theta, you can think of it as a composition of sorry. So each theta one corresponds to what percentage of the topic does the document have. Okay. Theta two corresponds to what percentage of the document does the second topic have, belongs to the second topic. Essentially, what is the theme of the second, is does the document have the second topic theme or not? That percentage proportion is what theta is capturing. Okay. And then once you draw theta, keep it fixed. So what we're describing is a generative procedure of generating a single document. That's important. We're only going to generate a single document. So first we start with theta. Get a sample theta. Okay. Maybe it says finance is something, sports is something, and weather is something. Okay. And then let's say you want to generate an N word document, capital N word document. Then what we're going to do is proceed sequentially. We'll start with the first word. We'll first sample a topic for that first word. Okay. What is meant by sampling a topic for the first word? Just get a. We know that there are three topics, and there's a topic proportion. Let's say 0.5, 0.49, and 0.01, right? In the previous slide. Then you draw. So you want to assign a topic for each word here. Okay. So for the first word, I'll draw a sample. Maybe it happens to be weather. Okay. Then the first word has to be a weather topic word. Okay. That's what we are deciding. I've not decided the word, but I've decided the topic of the word. Okay. And then I can do that. I can do this in a for loop, figure out the topics for every word. Okay. And then what I do is I'll have another bunch of parameters. These are called topic distributions, or the topic vectors themselves. I know what topic it should be. I'll sample a word according to the topic. Okay. What does it mean? I have three topics, right? So I'll have three beta vectors: beta 1, beta 2, and beta 3. Okay. And what is the length? The number of words I have. Okay. What are these beta 1, beta 2, beta 3 vectors? They are also probability mass functions. Okay. When I say, if you look at this equation, when I say I sample a word, all I'm saying is if beta 1 is the finance topic, okay, then it has different probabilities for different words appearing in my vocabulary. Let's say my vocabulary has 1,000 words. Okay. It's just saying that beta 1 is essentially a probability mass function where most of the probability mass is concentrated on those words which are related to finance. Okay. And if it's sports, there will be a bunch of sports in my vocabulary, sports words in my vocabulary. If beta 2 is a topic, then there will be most of the words which are related to sports will have higher probability mass. Okay.
But does one word, for example, in the first row, does
Could
this
be part of-
probability sum up to 1 across 3 topics?
No.
Okay.
These are three different probability mass functions. They're no relation to each other. Of course, the sum of all the entries in this vector should be equal to
So
1.
the same word can have
High
high
probability.
probabilities on 2. for
All three.
example.
Yeah, two. Yeah.
Okay.
So, okay, I'm just describing the generative process as I told you. I haven't told you how we're going to learn whatever parameters are there in this model. Okay, I'm just telling you how would a document be generated. Okay, is this fine? So first we generate a topic distribution for the document, then we assign placeholder topics for every word in the document, and then actually get the words of the document. Okay, and then so this is the generative process. Now, actually, let's come back to the original question. We already have documents. We want to get topics for the document. So we have to do the opposite, right? So we given the documents, now we are asking what would be the topics for each of the document, actually, right? So to do that, you need to know the parameters of this model. What are the parameters of this model? Alphas are the parameters of this model, and these entries in this vectors are the parameters of this model. Okay, and also, of course, how many topics you don't know. Like you can also choose. Oh, there are 5 topics in this corpus. In this corpus news articles. Maybe there are 100 topics in this news article. That's also something you need to choose. Okay. So those are the parameters that you need to learn. Learning them is a hard task. So we will see if we can get there when we talk about graphical models. Okay. Yeah. So I guess these are all illustrators to show you like this is what I said, like a huge list of same. I mean, here it's not the same words, but it's just showing the top words in each topic. But basically, betas are like this. Okay, beta 1, beta 2, beta 3, and then each word is supposed to be belong to some topic, and they have highlighted the topics. I mean, the word topics there. Okay. like the orange or pink ones and the yellow ones and so on. Okay. Anyway, these are just illustrations. Uh, yeah, and so here is a plate notation. So as I said, it is a graphical model. So things outside the plate notation are the parameters, the alpha and beta. And what does this plate look? This plate is about for each document. For each document, let's say I have capital D documents, capital D news articles. For each document, I get a theta D sample. So everything inside is a random variable. Okay, so this is a random variable. I get a topic distribution, and then for that document there will be n words. I mean, in this example, there will be capital N words on every document, and so I'll create the topic for each word and then the word itself. Okay, and these arrows are just saying what are the parameters needed to get those realizations of those random variables. Okay, so um, yeah, and that's called latent digital allocation. What's latent? We only observe words. Okay, we only observe the documents. We don't know these intermediate random variables are latent. So Z is a latent random variable, and the topic distribution of that document is a latent random variable. Latent just means hidden. Okay, it's not measured. Okay. Any questions? It's a bit too fast, I understand, but we will revisit this in the graphical model section again. Okay, so this is just an example of like how people have been working with text. Let's say before deep learning, not before deep learning, but recently. Yeah.
I have one question. If you were doing this in practice,
Yeah.
And you had like say some words that were really common,
Yeah.
did you try to purge those? If
Yeah.
they were like, I don't know what fraction would be, I don't know, sensible. If a word came up in more than half of your documents, would that be something?
Yeah,
you'd
yeah, yeah.
extract?
So I think words follow Zipf's law or something, right? There's
I don't know.
a distribution of like how frequent the words are. Like you can draw a histogram of how frequent the words are. Um, you can look at your corpus, get all the unique words. That's your vocabulary for at least that corpus. And then you look at the frequency count each of the words. Maybe there are words which are like extremely frequent and they're really like compared to some other words which are like extremely rare. You can actually drop both on both sides. Okay, because the ones which are extremely rare may uniquely identify a topic, but at the same time, they just increase the number of parameters you need to keep. Okay, and of course the words which are too common, like pronouns, for example, not pronouns, like these articles, right? So you can drop them. There's some pre-processing, post-processing you would do, and in fact, the consideration is like how many to drop and all that. Those are all design choices we're not talking about here. Yeah. Okay, this next slide is actually, so what I did was I actually introduced directly the LDA model. What would be an even simpler model? So let's say somebody came up with this LDA model back in 2003. Okay, after a lot of research or whatever, a lot of development, right? We are only seeing the outputs, the final things, which are pretty complicated. So a simpler version, a simpler topic model would have been like this, where there would be a topic distribution that would be the parameter, and then my generative process would be get a topic from that topic distribution, just say sports, and then just keep sampling words from that sports topic distribution. That's it. So it's a single topic model, where first you draw for a document what topic it belongs to, and given the topic, keep drawing whatever capital N words for that topic. Okay, if it's a sports topic, keep drawing sports words. If it's a finance topic, keep drawing finance words. Okay, so this is this model. This is model. It's called a mixture model. Mixture because there's a fixed topic distribution which is actually a parameter. Here this is called an admixture model because the topic distribution is actually document dependent and is changing. Okay, I mean it's a random variable. So anyway, just some names I'm throwing out, but this is one example of an NLP task, topic modeling. Okay. Any questions about that? Wow, oh, we have time. So next we'll come back to where we left off. I guess we saw a lot about CNNs last time. So we'll see one example of using CNNs for sentence classification. The same, sentiment analysis, sentence classification. They are all the same task. Okay. So here, what is the input? It's a sequence of words, right? The sentence has a structure, and the output is a label: positive sentence, positive class, or negative class. First baseline. What's the best thing you can do? I mean, if you do not know deep learning or anything about text, ignore the sequence. Okay. And basically ignore the semantic information. in the sense that what do the words mean? No idea. Treat the input as a fixed length of a bag of words. Okay, it just means that these are the words that were present in this sentence out of all the vocabulary that I have. Okay, and so think of, if the word is present, indicate it to 1. If the word is not present, indicate it to 0. Okay, think of a binary vector, which is the length of the vocabulary, and only those words which are present are ones. Where am I going with this? Think of the name-based classifier. Okay, you have a fixed size input, w1 to wn, and you just want to classify it as spam or not spam. In this case, positive class or negative class. Okay, so that's baseline. You're not really exploiting any information about sequence aspect of the model, the sequence aspect of the sentence, all semantic information, the words. Okay, it's just name-based. What I described here. Clear? Okay, so second baseline is you can have instead of weighted average of word vectors. So I didn't tell you what word vectors are. Okay, let's skip this. This is just a slight variation. Let's get to CNN. So just recall what the CNN operation was. In fact, we'll only recollect, we'll only need the non-tensor version of this, okay, in the sense that what was CNN doing? So this model came about in 2014, 2015, okay, and it's a little bit old now in terms of how things go about in this field. But so what is the convolution aspect? So if I had a tensor, let's say in this case an image, and I had a filter of a certain size 3x3, then what I would do is it will have a bunch of numbers. Those are my parameters, and I would multiply it element-wise with spatial regions of my input, right? And then I would take a stride of 1, multiply, and take a stride of 1, multiply. That's what I would do, right? And if there were depths, then the filter would also have the same depth as the input depth, right? That's a CNN operation. Just I'm recollecting what the operation is. Now, I just want to motivate why CNNs make sense for sentences first, and then look at the actual construction of the CNN classifier, CNN-based sentence classification classifier. So CNNs capture already, in images, what do they capture? They capture some sort of local patterns in the images in the lower level layers, and hopefully more complex patterns in the higher level layers. Okay, so and then they also capture this patterns are essentially composition. Like it's as if the upper level layers are composing the smaller level patterns. Okay, like edges and curves and so on. It's getting composed to form like the silhouette of a like a swan or something, whatever is the class. So this type of a structure can potentially also be used for sentences, because sentences also have some locality aspect, right? So words near to each other may suggest something compared to if the words were too far away, right? So the locality aspect is also there. And for example, if there's something negative in the sentence, whether it's at the beginning of the sentence or the back of the sentence, may tend to mean the same thing. I'm not saying it's a rule, but so that's what CNNs that motivates us to use CNNs for this. And the idea is first thing, input. What is the input? What is the input? The input is going to be the sentence. In this case, is going to be transformed into a matrix. Okay, and there will be one row for each word. Okay, so if the sentence has 10 words, or actually in the next example, if the sentence has 7 words, then there will be one word per one row per word. Okay, and what will be the matrix? What is the matrix size? In this case, let's say 7 words, including the exclamation mark here. So there's one row per word, but what are the contents here is actually, we'll talk about in the third part, where we talk about word to vec. Okay, think of these as some vectorial representation of the word. Okay. For example, in this here it wouldn't make sense, but for example, this could be just a binary encoding of the word. Like let's say the number of columns. Not in this example, but if you think of the number of columns as the vocabulary size, then it's just a one-hot encoding of like the coordinate is 1 if that word is that that word. Okay, you can do that, but it doesn't matter. Here it just chosen D to be 5, as in the number of columns to be 5. So that's the input. So first thing, step 0, a sentence has been converted to a matrix. where the entries of the matrix, entries of the rows are either word vectors, which we will see for quite a bit of time next, or just think of it as a one hot encoded version of the um, uh, of your word. Okay. Now, once you have the word, here is full CNN. So it has one. Uh, it just has one layer. I think. Yeah, it has one layer, one fully connected layer, and output. Okay. So let me show, I guess, how this is working. Okay. So the things in these color boxes. Okay. These are actually filters. Okay. These are filters whose number of columns is the same as the input tensor. So in this case, the tensor is really a matrix. Let's forget about all the tensor complication. This is a matrix, and now I have a filter whose height is kind of important. You know, the difference between these filters. So there are 1, 2, 3, 4, 5, 6 filters here. The difference between these filters is just the number of rows in each filter. Okay, the width is the same. Okay, so how do you? So what do you do? Multiply this with this. Okay, you get one entry. You can't really slide to the left or right. You can only slide below. So slide one step below, and you get second entry. And slide one more step below, third entry. Slide one more step below, fourth entry. Okay. You can't slide horizontally. The only thing you're doing is slide vertically. Okay. But you're just doing element-wise multiplication. Okay. Same thing in the second filter. So you're getting two. So these are the output activation maps. They only have one dimension because the width is the same as this width. So you can the output activation is not really 2D. It's just a vector. Okay. Yeah. So I mean, you can have any. So this is just illustration. Okay. So you can have many filters of the same size, for example. It doesn't have to be two. Here it's just two filters of certain size, two filters of some other size, two filters of some other size. But you don't have to have two or anything.
Is it like with the image where it's trying to find like the lines and the edges?
Yeah. This is basically the motivation is to have some temporal aspects captured by these weights. Okay. It's not so much about lines. I think. I mean, it's kind of hard to.
Obviously, just,
Yeah.
but it is kind of trying to find patterns. In this.
Yeah, it is trying to capture the same idea as the local invariance idea. So maybe I like this is kind of a pattern that you want to capture to say that the sentiment is one. So maybe a filter which has a vision of like looking at all these three words can actually suggest that the neuron which says positive should fire or something. So, yeah, it's same idea. So here I'm saying is you have these six filters, you slide them, you will only get vectors, and then you do max pools out of these four numbers, get one number. You know, it's a very illustrative example. Four numbers to one number. In this case, I guess five numbers to one number, and so on. Anyway, you got one number after the max pool operation. Then from these, let's say after max pool, you concatenate all the outputs, and then do a what is it called the final weight matrix to get to two classes. Binary two class classification, right? So you get two scores, and then you do a softmax operation and figure out what the score is. This is just an illustrative example. You can look at those papers, and in fact, on the syllabus page, I have the two papers linked. It's easy to read, just to get you a flavor of the research is not too far away from what you're doing. Okay, some of the research at least. Okay, so it's a very easy to read paper, simple idea, and since you have spent so much time on CNNs, it's at least easy to read. Okay.
Is
Yeah.
it still do like if you have activation functions, it's still the same activation functions like prelude?
Yeah, same idea. Yeah. Actually, I don't remember. So let's see. Actually, this is a simpler paper. Yeah, literally the title of the paper was CNN's for sentence classification from 2014, and what activations? Good question. I don't think I can eyeball it here. Oh yeah, yeah. So here he says f is a nonlinear operation such as a hyperbolic tangent. So I don't know if he's talking about ReLU, but yeah, it's just a 4-page, not 4-page, 6-page paper, and then they really show for sentence classification how they're performing with respect to so many other methods. Okay, so this is the CNN methods, and they can show that they're able to do really good classification, accuracies, let's say 80s or whatever 90s compared to many of these other methods. Okay. I mean, some of the methods you already know, like I guess this is probably SVM with some feature engineering. SVM literally, yeah. Anyway, it's a very short paper. Have a look at it. Um, but this is CNNs for classification. CNNs for sentence classification. Any questions? Yeah.
I made it. So what goes into the 7 by 5 matrix, original matrix?
Yes. So we will talk about what goes in here when. So I gave you one example where this vector. Think of it as like the vocabulary length. Like let's say whatever is the vocabulary. Let's say 10 words are in my vocabulary.
In the entire document?
Yeah, in the entire universe, like maybe 50,000 if you want to be realistic. Let's say there are 50,000 words in the English vocabulary. Then think of this D as 50,000 length, where it could be one hot encoded, where one coordinate is one. If think of the dictionary ordering of the words, and if the word, let's say, apple appears, then maybe the 15th coordinate is one and everything else is zero.
Oh, so it's just going to be a row of all
That's
zeros.
one example, but yeah, that's one example of what it can do. Each row is like a word specific vector. Okay. I just told you that the word specific vector is in this case example vocabulary length, but the rest of today's lecture is about what is the right word vector here. Okay, so that's what we're going to talk about. Word embeddings. Okay, it's a very nice concept, not extremely new, but very nice concept. We'll study, okay. And they give a lot of. So it's a simple question as, for example, you can use a vocabulary length one hot encoding vector. You'll get some classification performance. You can drop them and use what are called word vectors, which we'll learn separately. We'll learn next. If you drop the previous representation, use a different representation, you'll actually improve the performance. So they're actually like some sort of a pre-training on these right type of vectors actually. Okay, the vectors capture somehow the new vectors capture semantic meaning, whereas the one hot encoding things don't really capture semantic meaning. Because if you have the one hot encoding vectors, the difference between cat and dog in terms of vector distance, let's say Euclidean distance, is let's say 2 units. The difference between cat and house is also 2 units because just 2 coordinates are different, right? So there's that which is not captured. Anyway, so we'll get into embeddings pretty soon. We'll take a break soon as well, but I just want to see if I have a. Yeah, we do have a. So so this is the repo. I just so do you guys actually know how to clone a repo? So who doesn't know how to clone a repo? Okay, so let me see syllabus page. So I said this is the link. So this is a tutorial on using CNN for sentence classification. What we just saw for the past 5 minutes. This is the link. Now, if you click on the link, right? Some of you know this, so sorry about it. So this is the link, okay, and this is a repository, okay. This is a repository on GitHub. So it says on the top right, clone or download, right? So you have this link, okay. So if you wanna, you can actually download the zip itself if you want to, but we're not going to do that. We're going to copy this, and then we're going to go into our. Okay, this is my local directory. Okay. So you can just do git clone. That's the URL, and that's it. I don't know if git works here. Yeah, that's it. That's called cloning repository. You'll see a bunch of information, but okay, let me actually do it again. So let's see. There's nothing here, right? There's just downloads and Teja. Whatever. Two files. So I'll just do the same operation, same cloning operation, and then you'll see that there's a folder, PyTorch sentiment analysis. That was the name of that repository. And if you can go into the repository, you'll see all the same. In this case, there are notebooks. the example notebooks that you'll see, and you can actually look at like for example, it shows you this repo is a clone of or a clone or whatever copy of which repo. So this is the GitHub link from which we actually cloned it. Okay, and you can actually do 100 different things. Maybe next lecture I can give you a short tutorial and get, or if you want, you can learn it yourself. It's a fun thing to learn. So anyway, we cloned the repo, this repo, on my server side. I didn't want to clone it there because it's already there. So not this one, and it has a lot of things that, so it's all about sentiment analysis, but different ways to do sentiment analysis. Okay, and one of the ways that we'll see today is convolutional network based. And in fact, next lecture we're talking about RNNs, which are called recurrent neural networks, or LSTMs, or whatever. You must have heard of these. The other notebooks about these other techniques. Okay, so if you look at I think I opened this, right? Yeah. No. So it's a nice tutorial. It's literally the same as that paper and what we saw today. So, and in fact, it uses torch. So you should get more familiar with this. And in fact, it uses torch text. Okay, this is not installed by default. So you should do conda install conda, not conda, pip install torch text, or you can also do conda, but it has a longer command. You can just check what the command is. So it's the usual thing, get data. There's some really good just like data loaders and transforms in the case of vision. There's these data field and label field aspects here. Train data and validation data split. And in this script, at least, there's already something. You asked what is the dimensionality d, what is that vector representation there, right? For each word, for example, I, what was the 5-dimensional vector? In this case, they use something called glow vectors. These are 100-dimensional vectors. Okay, we will see. Actually, we'll go into the details after the break, but they use those vectors. Okay, but you get it through this command, and then the rest of the stuff is the same as before. Okay, once you have the training data and the vectors, okay, then it's a question of setting some batch sizes, device set it to CUDA, and then you have, and they have some functions. Okay, torchtext has some functions to deal with generating next, the batch sample. Okay, of certain batch size, the next batch. Okay. I think data loader is the equivalent in the vision side. Anyway, so this is the same idea, and I'm just showing you, like, I won't run this. I mean, I can run this, but I will not waste time. So it's the same idea. .NN, and then .module extends to CNN, and CNN has some, that embedding thing. Remember that embedding is that initial sentence matrix, and you have a couple of columns here. There's 3 columns. And then a linear layer, and then the forward operation is run your text through the embedding layer, and then the convolution operations. Okay. Anyway, you should, when you have time, go through this, run this, and let's take a break for 10 minutes.